You know, when we talk about motion, we usually think in simple numbers, right? How fast something's going, how far it went, how long it took. But what if I told you that to really get a grip on the world around us, a simple number isn't enough? Sometimes you also need to know which way. And that right there is the huge difference we're going to dive into today. So let's jump right in with a little puzzle. Picture a hiker. We'll call him Eric. He walks a steady 11 kilometers north, takes a right turn, and then walks another 11 kilometers east. All told, he's covered 22 kilometers. Simple enough. But here's the real question. Is he actually 22 kilometers away from his camp where he started? Now, your gut instinct might be to say, yeah, of course. But physics, well, it has a much cooler answer. To crack Eric's puzzle, we first have to get a handle on a core concept in physics, the idea that we have two totally different ways of describing quantities. It sounds simple, but this is the key that unlocks everything about describing motion properly. And here they are, scalars and vectors. And honestly, the difference is pretty straightforward. A scalar is just a number. It tells you how much of something there is. But a vector is way more powerful. It tells you how much and which way. Seriously, just think of it as a number with an arrow attached to it, pointing the way. Okay, let's zoom in on scalars first. A scalar is all about magnitude. It's just a number. That's it. Remember when we said our hiker walked a total of 22 kilometers? That distance is a perfect textbook example of a scalar. It's just a value, no direction needed. And now for the real star of our show, the vector. A vector absolutely has to have both a magnitude and a direction to be complete. This is exactly what we need to describe the hiker's final position, which has a special name, his displacement. See, displacement isn't about the long, winding path you took. It's the straight line distance and direction from your starting point to your finishing point. All right, now that we've got those definitions straight, let's get back to Eric out there in the woods. We're going to use what we know about vectors to figure out the how far part of his journey, what we call the magnitude of his displacement. And guess what? The perfect tool for this job is something you probably remember from math class, the good old Pythagorean theorem. It's the absolute best way to add two vectors together when they form a right angle. And what do you get when you combine a path north and a path east? A perfect 90-degree angle. So let's walk through it together. We've got our two vector paths, 11 kilometers north and 11 kilometers east. We can plug those right into the formula. A squared plus B squared equals C squared. So that's 11 squared plus another 11 squared. That gives us 242. To find C, which is that straight line distance, we just take the square root of 242. And the answer is, drumroll please, 15.6 kilometers. This is that aha moment. He walked 22 kilometers, but as the crow flies, he's only 15.6 kilometers from where he started. That's the magnitude of his displacement. But hold on, we're not done yet. Remember, a vector with just a number is only half the story. So we've nailed down the how far, but we're still missing that second, equally crucial piece of the vector puzzle. We need to solve for the which way. We need the direction. Now, to get the precise direction, we'd normally pull out another trusty math tool called trigonometry. We're not going to get bogged down in all the calculations here, but that's how physicists and engineers would find the exact angle of the hiker's final position relative to his camp. But here's the beautiful part about our specific problem. Because Eric walked the exact same distance north as he did east, the result is incredibly simple and elegant. The direction is perfectly northeast, a clean 45-degree angle right between north and east. And there you have it, the complete, satisfying, final answer. Eric's displacement is a vector, 15.6 kilometers in a northeast direction. We have the magnitude, the how much, and we have the direction, the which way. That, my friends, is a complete vector. Okay, so you might be thinking, that was a fun little math puzzle, but what's the big deal? Well, it's a huge deal. This difference between a simple number and a number with direction is absolutely critical in, well, pretty much everything in the real world. Just think about it. A pilot can't just know their speed. They need to know their velocity. That's speed plus direction, to deal with crosswinds that are trying to push them off course. Or think about a meteorologist tracking a hurricane. Sure, its speed is scary, but its direction is what tells you whose homes are in danger. In situations like these, which way isn't just an extra detail. It can literally be the difference between life and death. So if you take one thing away from this, let it be this. Whenever you're describing something moving or a force acting in the physical world, just ask yourself one simple question. Does direction matter here? If the answer is yes, then you know you're not just dealing with a plain old scalar. You're dealing with a vector. And that leaves us with one final thought to chew on. Where else in your everyday life do you see things that just don't make sense without knowing the direction? I mean, think about giving a friend directions to your house, or kicking a soccer ball to score a goal, or even the force of gravity that's pulling you down right now. Once you start looking for them, I promise you'll start seeing vectors absolutely everywhere.